Welcome back to Advanced Skills Learning. Gen AI prototypes are easy. Production systems are hard. In this series, we focus on the decisions that determine whether your system actually works at scale. Today, we're talking about a hidden performance killer in RAG systems, the reranker. RAG systems often feel intelligent. The answers look sharper. The top document seems more precise. But then something happens in production. Responses feel slower, latency creeps upward, infrastructure costs rise, and suddenly your quality improvement has become a scaling problem. The reranker is usually why. Retrieval is fast because it uses embeddings and approximate nearest neighbor search. That's optimized vector math. It's designed for scale. Generation is manageable because you control model size, token limits, and streaming behavior. You can optimize prompts and responses. But reranking is different. It runs a deeper model, often a cross-encoder, on every candidate document you retrieved. And that changes everything. A reranker compares the full query with each candidate document individually, not as vectors, not as dot products, but as combined token sequences processed through attention layers. That means real transformer compute. And it does this once per document. If you retrieve 10 documents, that's 10 forward passes. If you retrieve 50, that's 50 passes. The scaling cost is linear in K, but the performance impact feels exponential. Now here's why teams love rerankers. They genuinely improve precision. The top result is often more relevant. Edge cases improve. Semantic nuance improves. For compliance systems, regulated environments, or high-stakes Q&A, this can be extremely valuable. For demos and early pilots, this feels like a breakthrough. And in small systems, it is. But production traffic changes the math. Now let's look at the scaling trap. If your top K is 5, that's 5 model passes, latency may be acceptable. If your top K is 20, that's 20 passes, your P95 latency stretches. If your top K is 50, that's 50 passes, and now your system becomes unpredictable. The problem isn't obvious because retrieval still looks fast. The bottleneck hides in the middle of the pipeline. Quick check. 2 seconds. What grows linearly with K? A. Embedding size. B. Reranker latency. C. Token limit. Keep your guess. The answer is B. Reranker latency. Now let's understand why cross-encoders are expensive. Embedding retrieval compares fixed-size vectors. That's efficient and parallelizable. But a cross-encoder runs attention across both query and document tokens. Every query token can attend to every document token. That means the model must consider interactions between every query token and every document token. This is fundamentally heavier than embedding similarity as it creates significantly more computation per evaluation. And remember, this happens for every candidate document. So even if each pass takes only 100 to 200 milliseconds, multiplied by 20 or 30 documents, you are suddenly adding several hundred milliseconds, sometimes more than a full second, before generation even begins. And that's under light load. Under real traffic, the reranker becomes a latency multiplier. Each user request now contains multiple model executions. Those executions compete for GPU resources. Requests queue, throughput drops, autoscaling tries to compensate, and your latency distribution develops a long tail. This is where production systems break. Not at average latency. At P95, at P99, that's where timeouts occur. That's where users refresh the page. That's where SLAs are violated. That's where infrastructure costs surge because autoscaling tries to compensate. And because reranking sits between retrieval and generation, it silently blocks the entire pipeline. So when does reranking actually make sense? When precision is mission critical. Legal research, compliance review, medical decision support, environments where returning the wrong top document has serious consequences. Even then, constrain it. Keep top K small, 10 or less is usually manageable. Measure latency impact continuously. Monitor P95, not just averages. And test behavior under load, not just in isolation. Now let's talk about smarter architecture patterns. Stage 1. Strong retrieval. Combine vector search with keyword search. Tune hybrid weights deliberately. Improve chunking strategy. Ensure embeddings reflect the domain vocabulary. Stage 2. Filtering. Use metadata constraints to eliminate irrelevant candidates early. Date ranges. Document types, user permissions, anything that reduces the candidate set before heavy computation. Stage 3. Optional light reranking on a narrowed set. Notice the order. Narrow first, compute later. Quick check. 2 seconds. What's the safest first optimization? A. Increase top K. B. Add more GPUs. C. Reduce candidates before rerank. Keep your guess. The answer is C. Reducing candidates reduces both latency and cost. That's architectural thinking. Here's the key mindset shift. Rerankers are precision tools, not default components. If you use them, measure their marginal gain in relevance versus their marginal cost in latency and infrastructure. If the gain is small, remove them. If the gain is critical, constrain them. Production Gen AI systems are not just about intelligence. They are about balance, precision versus speed, quality versus throughput, architecture versus convenience. Rerankers are powerful, but power without boundaries becomes a bottleneck. Design deliberately, measure rigorously, scale intentionally, and that's how Gen AI systems actually work. Thanks for watching. If this video helped, like the video and subscribe to Advanced Skills Learning for more Gen AI explainers, practical architectures, and quick quizzes to test your understanding.